Hello everyone, welcome back. In this video, we'll be taking a look at subsequences and the Bolzano-Weierstrass theorem. So first we'll look at subsequences. So what's a subsequence? This is the formal definition of a subsequence. So let an be a sequence of real numbers, right? So let an be any sequence, and let n1, which is less than n2, less than n3, less than n4, less than n5, be an increasing sequence of natural numbers. So this sequence n1 is less than n2 is less than n3 is an increasing sequence of natural numbers. Remember, the definition of a sequence is any set of numbers with domain as the natural numbers. Then the sequence an1, an2, an3, and so on is called a subsequence of the sequence an. So let's look at an example to see what's really going on here. So consider this sequence an, which is denoted, which is 1 over n, and these are the terms of the sequence. Then 1 over 2, 1 over 4, 1 over 6, 1 over 8, 1 over 10, 1 over 12 is a subsequence of the sequence an. And similarly, 1 over 10, 1 over 100, 1 over 1000 is a subsequence of the sequence an. So I want you guys to notice that the order of terms in a subsequence is the same as in the original sequence. No repetitions are also not allowed. So we can't go from 1 over 4 to 1 over 6 back to 1 over 2. The order should be the same as in the original sequence, and you cannot repeat. We can't go from 1 over 2, 1 over 4, 1 over 6, and then again 1 over 6. Repetitions are not allowed. So a subsequence is just a sequence of numbers that are selected from the original sequence. So let's take a look at a very useful theorem that comes from this. So the subsequence theorem. So subsequences of a convergent sequence converge to the same limit as the original sequence. So if you have a sequence converging, so let an be the original sequence converging to a limit a that tends to a limit a, then the subsequence of this sequence an will also converge to the limit a. So when we do the proof of this, we let an be a sequence that converges to a. So now we have to show that a subsequence a and k also converges to a. So let a and k. So note that subsequences are denoted as such a and k. So we have to show that this subsequence also converges to a. So let a and k be a subsequence of a and. So let epsilon be greater than 0. This is our template of the proof. Remember, we seek n such that for all k greater than n, because k is the index of the subsequence, so for all k greater than n, a and k minus a, because the subsequence should also converge to the same limit, a and k minus a should be less than epsilon. So before we go with the proof of this, I want you guys to note that a1 is so if we have original sequence a1, a2, a3, a4, a5, and so on and so forth, and we choose the subsequence and we choose a subsequence of this sequence such that we choose this term as a subsequence, this term as a subsequence, this term as a subsequence, then we get the subsequence. This is the sequence and this is the subsequence. We get the subsequence as an1, an2, an3, and so on and so forth, with an1 representing a1, with an2 representing a3 of the original sequence, and an3 representing a5 of the original sequence. So if you notice, and let's look at another example. If you have a sequence and a subsequence, such that A1, A2, A3, A4, A5, and we have a subsequence like AN1, AN2, AN3. So remember that we can always choose a subsequence as the sequence itself. We can, for example, this subsequence is an interesting subsequence, but it is allowed. In this subsequence, AN1 represents A1, AN2 represents A2, AN3 is A3, AN4 is A4, AN5 is A5. So this subsequence is a sequence of itself. So if you've noticed that this N1, N2, N3, N1 is greater than or equal to the 1. And where do I get this 1 from? From the original sequence. This is the one I get it from. And we notice that N2 is greater than or equal to 2. And N3 is greater than or equal to 3. Because in this first sequence we notice here, we get that N1 is equal to 1. We get that N2 is equal to 3. And we get that N3 is equal to 5. And in this second sequence we did right here, we get that N1 is equal to 1. We get that N2 is equal to 2. We get that N3 is equal to 3 and N4 is equal to 4. So at the worst case, so we get that N1 is always greater than or equal to 1 of the original sequence. We get that N2 is always greater than or equal to 2. We get that N3 is always greater than or equal to 3. When we consider the first sequence, we get that N1 is greater than or equal to 1. We get that N1 is equal to 1, but we get that N2 is greater than 2. We get that N3 is greater than 3, but right here we get that N1 is equal to 1. So if you have noticed that the subsequence Nk is always greater than or equal to n, because N1 is greater than or equal to 1, N2 is greater than or equal to 2, N3 is always greater than or equal to 3, right from the examples we did right here. So we get that Nk is always greater than or equal to n, and therefore I'm going to complete the proof right here. I hope you guys are seeing this. So if k is greater than or equal to capital N, then, right, I'm running out of room here, let me do this right here, then Nk is also greater than or equal to n, because Nk is greater than or equal to k, and right, because here n is equal to k, this n is the same as k here. I'm just using different terms so that you don't get confused, or let me just use the same term. If n is greater than or equal to n, so Nk is greater than or equal to n, and n is greater than n, so n, the small n, is greater than capital N, so we get that Nk is greater than or equal to n. And that's what we wanted. And that's what we wanted right here. So we get, hence a and k minus a is less than epsilon. Therefore we get that a and k also converges to a when nk is greater than or equal to n. And this n is what we get from the original sequence, and this nk is the subsequence. So when nk is greater than or equal to the n of the original sequence, and we know that the original sequence converges, so there is some n after which all the terms in the original sequence enter the tube, enter where an minus a is less than epsilon, and that same n also works for the subsequence when nk is greater than or equal to n, and then we get a and k minus a is less than epsilon, and therefore a and k also tends to a. And we're done with the proof right there. So let's now take an example of how we can use this pretty nice theorem. So consider Bn with b being between 0 and 1. So we get that, so if you look at terms of the sequence, for example, if you make b to be 0.5, we get that b1 is always greater than b2, which is greater than b3, which is greater than b4, which is greater than b5. and so on and so forth, and it's bounded by 0. Well, why is this? Because if we take example as b as 0.5, or you can take any number between 0 and 1 and it will work. If you take 0.5 to the power 1, you get 0.5, which is greater than 0.5 square, which is 0.25, which is then 1 over 8, which is then 0.5 to the power 4, which is 1 over 16, and so on and so forth. So we get the sequence which is half, a quarter, a eighth, a 16th, and so on and so forth, which is getting smaller and smaller and is bounded by 0. It will never be less than 0. So from the monotone convergence sequence, we get a sequence that is decreasing and is bounded by 0. So the monotone convergence theorem guarantees that this sequence converges to a limit. So by MCT, the monotone convergence sequence, the limit L of the sequence exists. So I'm gonna take a subsequence of this sequence. So I'm gonna take this subsequence B2n, which is just the terms B2, B4, B6. So I'm taking a subsequence of this original sequence, and this subsequence can be denoted by B2n as Bn. So by MCT, we know the limit L of the sequence exists. So Bn converges to some L by MCT. And now we've taken a subsequence of this sequence. So we have to find the limit of this sequence. So we have to find this L. So I've taken a subsequence right here, and we know this Bn, and since and the subsequence theorem guarantees that if a subsequence exists of a sequence, then the limit of the subsequence converges to the same limit as the original sequence itself. So the limit of the sequence B2n is same as the limit of the sequence Bn, which we know is L. So we get that. So limit of the sequence Bn is L. The limit of the sequence Bn is also L. So we get that L dot L is equal to L because the limit of the sequence B2n is also L. So from this we get L is equal to L square, which can be written as L square minus L is equal to 0. And I'm going to simplify this as L minus 1 is equal to 0. So we get that L is equal to 0, or as L is equal to 1. And it's pretty trivial that L is equal to 1 is not possible. Therefore, L is equal to 0. So if you have noticed that in this example, I'm pulling a lot of different parts of the course. I'm using the monotone convergence theorem, I'm using the subsequence theorem, and the algebraic limit theorem to show that the limit of the sequence Bn, where B is between 0 and 1, is always equal to 0. So this, you can use this example, you can use this let's say lemma to show that whenever we have a Bn with B being between 0 and 1, then this sequence always converges to 0, no matter the value of B, as long as it is between 0 and 1. Now let's take a look at the Bolzano-Weierstrass theorem before we end this video. So the Bolzano-Weierstrass theorem states that every bounded sequence, so every sequence that is bounded contains a convergent subsequence. So as long as the sequence is bounded, it contains a convergent subsequence. Now we're not going to do the proof of this theorem, or we're going to do it later in the course. So let's take a look at how we can use the Bolzano-Weierstrass theorem to show that the sequence contains a convergent subsequence. So consider this sequence an is equal, which is equal to minus 1 to the power n. So the terms of this sequence are just 1 minus 1, 1 minus 1, 1 minus 1. So graphically it looks more or less like this: 1 minus 1, 1 minus 1. So it oscillates between 1 and minus 1. So I hope you guys can see this. We notice that this sequence is bounded between 1 and minus 1. So now the Bolzano-Weierstrass theorem says that every bounded sequence contains a convergent subsequence, and that is true in this case also. So this bounded sequence 1 minus 1, 1 minus 1 contains a convergent subsequence. So if we choose a subsequence as 1, 1, 1 and 1 and so on and so forth, so we get a subsequence, let's call it A and K, as 1, 1, 1, 1. So this subsequence of the original sequence also converges to 1. This subsequence A and K tends to 1. Since all the terms of the sequence are equal to 1, it of course converges to 1. And we get this from the Bolzano-Weierstrass theorem. So since we did a lot of theorems involving sequences, bounded sequences and convergent sequences, I'm just going to repeat the summary of all that. So note that every convergent sequence, so if every convergent sequence is bounded, so if a convergent sequence is bounded, if a sequence is convergent, then it's bounded. Then secondly, note that not every bounded sequence is convergent, because note this sequence as a whole. Note this sequence an to the power minus 1 to the an, which is equal to minus 1 to the power n. It is certainly bounded, but it doesn't converge, it diverges, it oscillates between 1 and minus 1. Although it has a convergent subsequence, the original sequence doesn't converge. So I'm going to say that again. So firstly, every convergent sequence is bounded. Secondly, not every bounded sequence is convergent. Note that, however, every monotone and bounded sequence converges. So we get that from the monotonic convergence theorem. And finally, from the Bolzano-Weierstrass theorem, every bounded sequence has a convergent subsequence. So hope you guys have enjoyed this video. See you next time.